Hello there, and welcome back to Bedtime Science. I'm really glad you're here tonight. Tonight, we are going to explore a world that is already inside the room with you, although nothing in the room appears unusual. The screen or speaker carrying this voice works because electrons are guided through materials according to quantum rules. The light around you arrives in indivisible exchanges of energy. The atoms in the walls remain stable because their electrons are not tiny planets following ordinary paths, but quantum patterns governed by a mathematics unlike anything visible at human scale. Quantum physics is often introduced as the strangest part of science. It is described through particles passing through two openings at once, cats suspended between life and death, and distant objects sharing correlations that seem to ignore the space between them. Those images are memorable, but they can also make the subject feel like a cabinet of disconnected mysteries. The deeper story is more coherent. At the end of the 19th century, physicists believed they were close to completing the basic picture of nature. Motion followed Newton's laws. Light traveled as a wave. Heat could be understood through moving atoms. Electricity and magnetism had been joined into one elegant theory. The remaining puzzles seemed small, like a few clouds near the edge of an otherwise clear sky. But one of those clouds came from something as ordinary as warmth. Imagine a dark cavity with a small opening in one wall. Heat the cavity, and light begins to emerge from the opening. At first, the glow is dim red. As the temperature rises, it becomes orange, then yellow, then increasingly white. Furnaces, stars, heated metal, and even the human body all emit electromagnetic radiation because they have temperature. By the late 19th century, physicists were trying to describe precisely how much energy a warm object should radiate at every wavelength. The measurements were clear. Classical theory was not. At long wavelengths, the old equations worked reasonably well. At short wavelengths, they predicted that the emitted energy should grow without limit. A warm object should pour an impossible amount of energy into ultraviolet light and beyond. Nature did nothing of the kind. The prediction became known as the ultraviolet catastrophe, although the catastrophe belonged to the theory, not to the furnace. In Berlin, Max Planck searched for a formula that matched the data. He was not trying to overthrow classical physics. In many ways, he was trying to rescue it. Planck found that the observed spectrum could be reproduced if energy was exchanged not in any arbitrary amount, but in discrete portions related to frequency. Higher frequency oscillations could exchange energy only in larger steps. Lower frequency oscillations could do so in smaller steps. The proposal was mathematically successful and conceptually unsettling. Nature, at least in these exchanges, seemed not to behave like a perfectly smooth ramp. It behaved more like a staircase whose steps were unimaginably small but real. Planck introduced a constant, now written as h, that set the scale of those steps. Its value is tiny, which is why quantum discreteness is normally hidden in ordinary life. A thrown ball carries energy in such enormous multiples of Planck's constant that the spacing between allowed quantum values is effectively invisible. For atoms and light, however, the steps matter. Planck initially treated quantization cautiously, almost as a formal device. Yet the small constant he introduced became one of the deepest numbers in physics. It appears wherever the quantum world meets the classical one. It helps determine the size of atoms, the energies of photons, the unavoidable spread between position and momentum, and the scale at which familiar intuitions begin to fail. A second puzzle came from light shining on metal. When ultraviolet or visible light strikes certain metal surfaces, electrons can be released. The effect was known before Albert Einstein explained it, and its details were difficult to reconcile with a purely classical wave. If light were only a continuous wave delivering energy across a surface, then brighter light should eventually knock electrons free regardless of color, provided enough energy accumulated. One might expect a delay, while weak light slowly transferred its energy. Experiments showed something different. Below a certain frequency, no electrons emerged, no matter how intense the light became. Above that threshold, electrons appeared without the expected delay. Increasing the brightness released more electrons, but increasing the frequency increased the energy carried by each electron. In 1905, Einstein took Planck's reluctant quantum step and carried it farther. He proposed that light itself exchanged energy in localized packets, later called photons. The energy of each photon depended on its frequency. A low-frequency photon might simply lack enough energy to free an electron from the metal. Sending more of those insufficient photons would increase their number, but not the energy of any one encounter. A higher frequency photon could deliver the needed amount in a single exchange. This explanation separated brightness from color in a precise way. Brightness largely described how many photons arrived. Frequency described the energy carried by each one. The metal did not gather a smooth trickle from the entire wave. An electron absorbed energy in a discrete event. Einstein's suggestion was radical because the wave nature of light was already supported by beautiful evidence. Light bends around obstacles. It diffracts through narrow openings. Two light waves can overlap and produce bright and dark bands through interference. These are wave behaviors, and they had helped establish the wave theory of light long before the word photon existed. So light now seemed to present two faces. In some arrangements it spread and interfered like a wave. In others it arrived in localized exchanges like a particle. The natural temptation was to ask which description was really correct. Quantum physics gradually replaced that question with a more difficult one. What if light is not secretly one familiar classical thing wearing two disguises? What if the categories of wave and particle are both approximations drawn from everyday experience, while the quantum object itself belongs to neither category completely? The old double-slit experiment made the tension visible. At the beginning of the 19th century, Thomas Young sent light toward two narrow slits and observed a pattern of alternating brightness and darkness on a screen. If light consisted only of tiny classical projectiles, one might expect two bright regions aligned with the openings. Instead, the light from the two paths combined. Where crests reinforced crests, the screen brightened. Where crest met trough, the light canceled, producing darkness. The pattern was a signature of waves. Much later, the experiment could be repeated with light weakened until photons arrived one at a time. Each detection appeared as one localized spot. Nothing spread across the screen as a faint classical wash. Yet as many individual events accumulated, the spots gradually formed the same interference pattern. That slow emergence is one of the quiet wonders of the quantum world. The first photon leaves only a point. The hundredth still looks like a point. But after enough arrivals, broad bands become visible, as though each localized detection had been guided by a wave-like pattern of possibilities. It is tempting to imagine each photon splitting like a tiny bead and then recombining. That image is too literal. Quantum theory assigns amplitudes to the possible alternatives, and those amplitudes interfere. The experiment does not allow a simple classical story in which the photon secretly chose one ordinary route while the unused route had no physical role. Yet it is also risky to claim that a small object traveled through both slits in exactly the same way a macroscopic object could occupy two corridors. Quantum language is careful because the familiar words were invented for a different scale. The pattern changes when the experiment is arranged to reveal which path was taken. If information about the slit becomes physically available, the interference is lost. This is sometimes described as human observation changing reality, but no conscious mind is required. A detector, scattered photon, surrounding gas molecule, or other interaction can carry path information into the environment. The important point is physical distinguishability, not a person staring at a screen. The double slit is therefore not a magic trick performed by awareness. It is a demonstration that alternatives combine differently when they remain coherent and indistinguishable than when information about them becomes recorded in the world. The mystery deepened when matter began behaving like light. For centuries, matter and radiation seemed to occupy opposite sides of a clear divide. Matter came in particles. Light traveled in waves. Einstein had shown that light could exchange energy in particle-like packets. In 1924, Louis de Broglie proposed the reverse symmetry. Perhaps matter had a wavelength too. The idea was daring and simple. If photons could carry momentum while behaving as waves, perhaps an electron's momentum could also be associated with a wave. De Broglie wrote a relation connecting wavelength with momentum through Planck's constant. For a large object, the resulting wavelength is far too tiny to notice. For an electron, it can be comparable to atomic distances. A few years later, Clinton Davison and Lester Germer were studying electrons scattered from a nickel crystal. Their apparatus had been damaged in an accident, and the nickel surface was heated during repair. The heating changed the crystal structure in a way that ultimately made the electron scattering pattern clearer. At certain angles, the electrons emerged with enhanced intensity, as waves do when reflected from regularly spaced planes in a crystal. The observed wavelength matched de Broglie's prediction. Matter had diffracted. A separate experiment by George Paget Thomson sent electrons through thin metal films and also found diffraction patterns. There was a pleasing historical twist. Thomson's father, J.J. Thomson, had helped establish the electron as a particle. The son helped demonstrate its wave behavior. Within one family, the electron had crossed the classical boundary between particle and wave. This did not mean that electrons were soft ripples of ordinary material. They still arrived at detectors in discrete events. They carried charge in indivisible units. Yet their probabilities spread, diffracted, and interfered. The electron was not alternating between being a little marble and being a water wave. It was revealing that both metaphors were incomplete. Once matter waves were taken seriously, the atom itself had to be reconsidered. Classical physics had a serious problem with atomic stability. If an electron were simply a charged particle orbiting a nucleus like a planet around the sun, it would be accelerating as it curved. An accelerating electric charge should radiate energy. The electron should spiral inward, and the atom should collapse in a tiny fraction of a second. Ordinary matter would not remain ordinary for long. But atoms are stable. They also emit and absorb light at sharply defined frequencies, producing spectral lines rather than every possible color. When the light from hydrogen is passed through a prism or diffraction grating, it forms a series of distinct lines, like a barcode written by the atom. Niels Bohr proposed an early quantum model in which the electron could occupy only certain allowed orbits and could emit or absorb energy when jumping between them. The model captured important features of hydrogen and introduced the idea of discrete atomic energy levels. It was not the final picture, and its little planetary tracks are misleading if taken literally. Still, it showed that the stability and spectra of atoms were connected to quantization. The deeper theory arrived through several routes at once. Werner Heisenberg developed a mechanics built from measurable transitions rather than imagined electron paths. Erwin Schrödinger developed a wave equation inspired partly by de Broglie's matter waves. Max Born recognized that Schrödinger's wave should not generally be interpreted as a physical material smeared through space, but as something whose squared magnitude gives probabilities for measurement outcomes. Different mathematical languages turned out to describe the same quantum structure. The result was not simply a more accurate version of the solar system atom. The electron in an atom does not circle the nucleus along a hidden miniature road. It occupies a quantum state, often represented by an orbital, a pattern that tells us how likely different measurement outcomes are and how the state can interact with light and other particles. The familiar pictures of fuzzy atomic clouds are not photographs of substance spread like mist. They are visualizations of probability density. Some orbitals are spherical, others form lobes, rings, or more complicated shapes. These forms arise from standing wave solutions around the nucleus, shaped by energy, angular momentum, and the three-dimensional symmetry of space. This wave-like structure helps explain why only particular energies are allowed. A guitar string can support certain standing wave patterns that fit its fixed length. An electron bound to a nucleus is not a literal vibrating string, but the analogy hints at the logic. Not every arbitrary pattern can persist. The mathematical wave must satisfy conditions that select particular states. The atom therefore becomes stable not because the electron follows a perfect orbit without losing energy, but because its lowest energy quantum state has nowhere lower to fall. The state is already the ground state. Quantum mechanics does not permit the electron to collapse into an arbitrarily tiny classical point around the nucleus, while keeping every other requirement unchanged. The stable matter around you is one of quantum physics' most immediate achievements. The chair, the walls, the air, and the body resting among them are possible because atoms have structure, because electrons occupy quantized states, and because the smallest constituents of matter do not obey the classical rules that seemed so complete a century ago. The quantum revolution did not begin with a desire to make reality strange. It began because warm objects glowed in the wrong way, metals released electrons according to the color of light, atoms refused to collapse, and spectral lines appeared where classical theory expected continuity. The strange theory was not invented for drama. It was forced into existence by ordinary experiments that would not agree with ordinary expectations. And as the new theory took shape, it introduced an object unlike anything classical physics had used before, the wave function. The wave function is often described as the heart of quantum mechanics, although it is not a heart that can be pictured directly. It is a mathematical object, usually complex-valued, that evolves according to the Schrödinger equation. From it, physicists calculate the probabilities of possible outcomes when a particular measurement is performed. That sentence can sound modest. Probability appears throughout ordinary life. Weather forecasts give a chance of rain. A shuffled deck gives a chance of drawing a certain card. A coin toss is uncertain because tiny details of the throw are not known. Perhaps, one might think, quantum probabilities simply reflect ignorance of hidden facts. Quantum experiments resist that comfortable interpretation. In classical probability, the card is already somewhere in the deck even before anyone looks. The coin follows one definite trajectory, whether or not it has been calculated. Quantum theory does not generally assign every measurable property a pre-existing definite value. A state can instead contain several possible outcomes in superposition, with amplitudes that can interfere before a measurement produces one result. The difference between probabilities and amplitudes is crucial. Ordinary probabilities simply add. Quantum amplitudes can reinforce or cancel one another, much like waves. The dark bands in a double-slit pattern are not places where particles merely happen to arrive less often. They are regions where alternative amplitudes cancel, driving the probability toward zero. This is why the wave function cannot be treated as a catalog of ordinary ignorance. Its phase matters. Two states with the same list of possible outcomes, but different relative phases, can behave differently when recombined. Quantum mechanics keeps track not only of how much possibility exists, but of how possibilities are related. Between measurements, the Schrödinger equation evolves the states smoothly and predictably. Given a wave function and the forces acting on the system, the equation determines its later form. The uncertainty enters when a measurement outcome is obtained. Quantum theory may predict the distribution of many results with extraordinary accuracy, yet it normally does not specify which individual result will occur in one trial. This combination is unusual. Deterministic evolution of the state, probabilistic appearance of particular outcomes. Consider a single unstable atom. Quantum mechanics can predict the probability that it will decay during a certain interval and can describe the exponential pattern followed by a large collection of identical atoms. But for one isolated atom, the theory does not provide a hidden clock showing the exact second of decay. Two atoms prepared in apparently identical conditions may decay at different times. Einstein famously disliked this fundamental role for chance. His phrase about God not playing dice was not a rejection of the successful calculations. It expressed a hope that quantum mechanics was incomplete, that beneath the probabilities there might be a more detailed level of reality restoring definite causes and outcomes. Other founders accepted the probabilistic structure more readily, although they disagreed about what it meant. Max Born's probability interpretation became indispensable. Niels Bohr emphasized that experimental arrangements define which properties can meaningfully be discussed. Heisenberg focused on relations between observable quantities rather than invisible classical trajectories. The arguments were not side conversations added after the mathematics was finished. They grew from the theory's central question: what, exactly, is the wave function describing? One possibility is that it describes reality itself. Another is that it describes information or expectations about future observations. Some interpretations treat it as a physical field in a high-dimensional configuration space. Others regard it as part of a rule connecting preparations to outcomes. The calculations agree even when the pictures differ. That is one reason quantum mechanics can feel both settled and unsettled. Its predictions are among the most successful in science. Its interpretation remains open. The uncertainty principle is another idea that is often simplified until its deepest meaning disappears. A common explanation imagines trying to locate an electron with light. To see something very small, one needs short wavelength photons, which carry high momentum. When such a photon strikes the electron, it disturbs the electron's motion. Measurement therefore changes the object, limiting what can be known. This story contains a useful truth. Real measurements involve interactions, and interactions can disturb systems. But Heisenberg uncertainty is not merely a problem of clumsy instruments. Even an ideal quantum state cannot possess an arbitrarily sharp position and an arbitrarily sharp momentum at the same time. The reason is woven into wave mathematics. A wave with one perfectly defined wavelength extends indefinitely. Because momentum is connected to wavelength, such a state can have sharply defined momentum, but it is spread across space. To create a localized wave packet, many wavelengths must be combined. The more tightly the packet is localized, the broader the range of wavelengths, and therefore momenta, required to build it. Position and momentum are linked like two different descriptions of the same wave pattern. Sharpening one broadens the other. The uncertainty relation gives a lower bound to the product of those spreads, set by Planck's constant. The principle does not say that nothing can be known. Quantum experiments can measure position with astonishing precision, or momentum with astonishing precision. What cannot be prepared is a state in which both distributions are infinitely narrow at once. Other pairs of quantities have similar relationships. Different components of angular momentum can be incompatible. Energy and time appear in several uncertainty relations, though time enters quantum theory differently from position. In each case, the structure reflects how the corresponding mathematical operations relate. The word uncertainty can sound like confusion. In practice, it is a precise statement about the shape of possible states. The quantum world is not vaguely blurry. It is constrained in a way that can be calculated exactly. This constraint helps explain atomic size. If an electron were squeezed ever closer to the nucleus, its position would become more localized, requiring a wider spread of momentum. That increased kinetic contribution resists unlimited confinement. The atom settles into a balance determined by quantum mechanics rather than collapsing under electrical attraction. The same principle echoes on much larger scales. In white dwarf stars, enormous gravity compresses matter until electrons are packed into states constrained by quantum rules. Electron degeneracy pressure helps resist further collapse. In neutron stars, related quantum effects involving neutrons contribute to supporting matter at densities beyond ordinary imagination. A relation born from waves and tiny particles, therefore, helps shape dead stars. Quantum physics repeatedly makes this journey from the microscopic to the cosmic. A constant too small to notice in a moving hand becomes essential in the structure of atoms, solids, stars, and the early universe. Erwin Schrödinger's famous cat was created to expose the unease in carrying quantum superposition from atoms into everyday life. Imagine a sealed box containing a cat, a radioactive atom, a detector, and a mechanism that releases poison if the atom decays. Quantum theory describes the undecayed and decayed possibilities in superposition before the event is registered. If the apparatus becomes entangled with the atom, the larger description appears to contain one branch in which the mechanism has not fired and another in which it has. The cat becomes tied to the quantum alternatives. Schrödinger did not invent this scene because he believed real cats casually hover in a mystical half-alive condition. He intended the absurdity to reveal a problem. If quantum mechanics applies universally, where does the smooth superposition described by the equation become the single definite world of experience? The cat dramatizes the measurement problem. In textbook language, a measurement causes the wave function to collapse to one outcome. But what counts as a measurement? Must there be a conscious observer? Is a detector enough? Does the environment continually measure systems? Is collapse a real physical event, an update of information, or a convenient rule hiding deeper dynamics? Different interpretations give different answers. The Copenhagen family of views emphasizes that quantum theory connects experimental preparations with possible outcomes, and that classical descriptions are necessary for communicating those outcomes. There is no single universally agreed Copenhagen doctrine, despite the label often being presented as one fixed set of beliefs. Bohr's writings were subtler than the slogan, "Shut up and calculate," a phrase usually associated with later attitudes rather than a careful summary of his philosophy. The many worlds interpretation removes collapse. The universal wave function always follows the Schrödinger equation. During a measurement, observer, apparatus, and system become entangled. Different outcomes occupy branches that no longer interfere effectively. Each observer within a branch experiences a definite result, while the total state contains all branches. This interpretation preserves the mathematical evolution but asks us to accept a vast branching structure of reality. It is elegant to some physicists and extravagant to others. Even within many worlds discussions, questions remain about how to understand probability when all outcomes occur in the universal state. Objective collapse theories take the opposite route. They propose that the Schrödinger equation is slightly modified so that sufficiently large or complex superpositions collapse spontaneously. In such models, the difference between quantum possibilities and classical outcomes is a real physical process, not merely an interpretive boundary. Experiments search for deviations from standard quantum mechanics that such models might produce. Pilot wave theories describe particles with definite positions guided by a wave. The wave evolves according to quantum rules, while the particle follows a trajectory influenced by the full configuration. These theories reproduce the ordinary predictions of non-relativistic quantum mechanics, but are explicitly non-local and raise their own questions when extended to quantum fields. Relational and information-centered interpretations take other paths. Some treat physical properties as meaningful only relative to interactions. Some understand the quantum state as representing an agent's expectations rather than an observer-independent object. Some place events, not continuously possessed properties, at the center of the picture. The remarkable fact is that scientists can disagree about these pictures while agreeing on nearly every laboratory calculation. Decoherence explains an important part of why the everyday world appears classical, even though it does not by itself settle every interpretive question. A quantum system is almost never perfectly isolated. It interacts with photons, air molecules, thermal vibrations, nearby electromagnetic fields, and the measuring apparatus. Through these interactions, information about different alternatives becomes dispersed into the environment. The system becomes entangled with countless external degrees of freedom. Once that happens, interference between large-scale alternatives becomes extraordinarily difficult to observe. The relative phases are not necessarily destroyed from the perspective of the universal quantum state, but they become inaccessible to local experiments because the information has spread into the environment. Imagine a dust grain illuminated by ordinary light. Photons scatter from it continually, carrying information about its position outward. Air molecules collide with it. Thermal radiation leaves it. Any superposition of noticeably different locations becomes entangled with an enormous number of environmental states almost instantly. To restore interference, one would need to reverse or control all those correlations with impossible precision. This is why quantum interference is easiest to observe in small, cold, carefully isolated systems. The larger and warmer an object becomes, the more channels connect it to its surroundings. Classical appearance is not necessarily a separate set of laws switching on at a certain size. It emerges because coherence is rapidly distributed beyond practical recovery. Modern experiments have pushed interference to objects far more complex than electrons. Atoms, large molecules, and clusters containing many atoms have produced wave-like interference under carefully controlled conditions. Each success extends the scale at which quantum coherence can be maintained. Yet a living cat interacts with its environment so overwhelmingly that the coherent overlap of macroscopically different states disappears on timescales far shorter than anything biologically meaningful. Decoherence helps explain why a table remains in one place, why a pointer shows one readable direction, and why the world does not look like a shimmering superposition. But it still leaves a subtle question. It explains why alternatives stop interfering locally. Depending on interpretation, it may not explain why one particular outcome is experienced rather than another. The quantum classical boundary is therefore not simply a line drawn at atoms, molecules, or visible size. It is a question of interaction, information, and coherence. The double-slit experiment can be understood again through this lens. When no path information escapes, the alternatives remain coherent and their amplitudes interfere. When a detector or environment records which slit is associated with which state, the alternatives become entangled with distinguishable records. The interference fades. Nothing needs to know the answer. The universe only needs to store it somewhere. This makes quantum measurement less mystical and more physical, though not entirely less strange. A measurement is an interaction that creates stable correlations between a microscopic possibility and a macroscopic record. A detector clicks. A pixel changes. A current flows. A memory forms. The fragile quantum alternative becomes linked to an outcome that can be copied, communicated, and remembered. In a sense, the classical world is the part of quantum reality whose information has spread widely enough to become durable. The next quiet surprise is that even properties we casually imagine as little internal arrows do not behave classically. The clearest example is spin. The word spin invites a misleading picture. It sounds as though an electron is a tiny ball rotating around an axis. But an electron is treated as point-like in the Standard Model, and its spin is not ordinary surface rotation. Spin is an intrinsic quantum form of angular momentum, a property built into the particle state. The strangeness became visible in an experiment performed by Otto Stern and Walther Gerlach in the early 1920s. They heated silver in an oven, producing a narrow beam of atoms, and sent the beam through a magnetic field that varied across space. A tiny classical magnet passing through such a field would be deflected according to its orientation. If the atomic magnetic moments pointed in every possible direction, one might expect the beam to smear into a continuous band on a collecting plate. Instead, the beam split into distinct parts. The results showed that the measured component of angular momentum did not take every value along the chosen axis. It was quantized. In the later language of electron spin, a measurement along an axis gives one of two outcomes, commonly called spin up and spin down. The words up and down do not mean that the electron carries a miniature compass arrow already pointing in one ordinary direction. A quantum state can be definite along one axis and become a superposition relative to another. If particles prepared as spin up along a vertical axis are measured along a horizontal axis, the results divide probabilistically. Measuring along the new axis changes which distinction is definite. This dependence on the measurement axis is not a defect in the particle's internal compass. It is the geometry of a two-state quantum system. Spinors, the mathematical objects used to describe spin one-half particles such as electrons, have a peculiar property. A full rotation of 360 degrees does not return the state to exactly the same mathematical form. It takes a rotation of 720 degrees to do so. The sign change after one full turn does not alter every isolated measurement, but it can be revealed through interference. Nature's smallest matter particles, therefore, carry a rotational structure unlike any ordinary arrow. Spin is not decorative. It shapes chemistry, magnetism, nuclear physics, and technology. The magnetic moments associated with electron and nuclear spin respond to magnetic fields. Magnetic resonance imaging uses the behavior of nuclear spins, especially those of hydrogen nuclei abundant in water and fat, to create detailed images of soft tissue. Inside an MRI scanner, a strong magnetic field slightly biases the orientations of many nuclear spins. Radio frequency pulses disturb that alignment. As the spins evolve and relax, they produce signals whose timing depends on the surrounding molecular environment. Magnetic gradients encode position, allowing the signals to be reconstructed into images. The scanner does not photograph organs with visible light. It listens to quantum angular momentum in the nuclei of the body. Spin also leads to one of the rules that makes matter occupy space. Wolfgang Pauli formulated the exclusion principle in 1925. Identical fermions, a family that includes electrons, protons, and neutrons, cannot occupy the same quantum state simultaneously. Electrons in an atom must therefore arrange themselves among available states rather than all collapsing into the lowest one. This rule helps build the periodic table. The first electrons fill the lowest energy atomic states. As proton number increases from one element to the next, additional electrons must occupy states distinguished by energy, angular momentum, orientation, and spin. The pattern of filled and partly filled shells repeats in a structured way, producing families of elements with related chemical behavior. Hydrogen begins with one electron. Helium completes the first shell with two electrons of opposite spin in the same spatial orbital. Lithium's third electron must occupy a higher shell, making it chemically more willing to participate in reactions. Neon closes another shell and becomes unusually unreactive. Sodium begins a new shell and echoes some of lithium's behavior on a larger scale. The periodic table is therefore not merely a catalog arranged by atomic weight or a clever organizational chart. Its repeating structure is a visible map of quantum states. The colors of transition metal compounds, the bonding patterns of carbon, the reactivity of halogens, and the stability of noble gases all depend on electron arrangements shaped by quantum rules. Chemistry is quantum mechanics expressed at a larger scale. The exclusion principle also contributes to the solidity of ordinary objects. When two pieces of matter approach, their electron clouds interact. Electrical repulsion matters, but so does the requirement that identical electrons cannot all occupy the same states. Rearranging them into allowed combinations costs energy. The result is a strong resistance to overlap. When a hand rests on a table, the atoms do not touch in the simple sense of hard classical spheres meeting surface to surface. Electromagnetic interactions and the quantum organization of electrons prevent the matter in the hand from passing through the matter in the table. The sensation of solidity is a quantum event repeated across an enormous number of atoms. Fermions are not the only family. Bosons, particles with integer spin, do not obey the same exclusion rule. Many bosons can occupy the same quantum state. Photons are bosons. This willingness to share states helps make lasers possible. At very low temperatures, atoms that behave collectively as bosons can gather into a Bose-Einstein condensate, forming a macroscopic quantum state. The contrast between fermions and bosons is one of nature's most important classifications. Fermions build the layered structure of matter. Bosons can crowd together and often serve as carriers of interactions or collective excitation. There is a deep relation between spin and statistics. Particles with half-integer spin obey Fermi-Dirac statistics and the exclusion principle. Particles with integer spin obey Bose-Einstein statistics. In relativistic quantum field theory, this connection is not an arbitrary rule added by hand. It follows from the structure required by quantum theory, relativity, and causality. A small label called spin determines whether particles avoid sharing a state or willingly gather into one. Pauli himself was known for unusually sharp criticism. Colleagues joked about the Pauli effect, the supposed tendency of laboratory equipment to fail whenever he came near. Beneath the humor was a physicist whose demand for consistency helped shape the foundations of 20th century physics. His exclusion principle first appeared as a way to understand atomic spectra. Its consequences later reached far beyond atoms. When a massive star exhausts its fuel, gravity compresses its core. In a white dwarf, electrons are forced into an increasingly crowded range of momentum states. Because they cannot all occupy the same state, the compression creates degeneracy pressure that can support the star up to a limit. If the remnant is too massive, electron degeneracy pressure is overcome. Further collapse can produce a neutron star, where matter is compressed until protons and electrons combine into neutrons and a much denser quantum state forms. Neutron degeneracy and nuclear interactions contribute to resisting gravity there. The quiet rule organizing electrons in a neon atom also helps decide the fate of stars. Quantum indistinguishability adds another layer of unfamiliarity. In classical life, two objects may look identical but remain individually trackable. Two coins can be numbered. Two billiard balls can be followed through a collision. Identical quantum particles of the same type are not merely similar copies. They are fundamentally indistinguishable. Swapping two electrons does not create a new physical arrangement that can be labeled by hidden names. The combined wave function must respond to exchange in a particular way. For fermions, exchanging identical particles changes the sign of the wave function. For bosons, it does not. These symmetries produce exclusion for fermions and enhancement for bosons. Sometimes what looks like a force is partly a result of this exchange structure. Electrons with parallel spin can avoid one another spatially in ways that alter atomic energies. Exchange interactions help create ferromagnetism, allowing many microscopic magnetic moments in materials such as iron to align into domains. A magnet lifting a paper clip, therefore, carries traces of quantum indistinguishability. Magnetism itself was difficult to understand classically. Moving electric charges create magnetic fields, but the permanent magnetism of materials depends heavily on electron spin, orbital quantum states, crystal structure, and exchange interactions. Atoms contribute magnetic moments. Their arrangement in a solid determines whether those moments cancel, oppose, form complicated patterns, or align strongly enough to remain after an external field is removed. The simple bar magnet is a collective quantum object disguised as a familiar household item. So is color. When light reaches matter, photons can be absorbed, reflected, scattered, or transmitted depending on available energy transitions and the material's electronic structure. A red object appears red because its molecules and electrons interact differently with different portions of visible light. Pigments absorb some frequencies and return others. Metals shine because conduction electrons respond collectively. Transparent materials allow visible photons to pass while still altering their phase and speed. Quantum energy levels determine which colors a molecule can absorb. Slight changes in molecular structure can shift those levels and transform appearance. The deep blue of one mineral, the green of a leaf, and the glow of a neon sign all emerge from electrons moving between or interacting within quantum states. The night sky also displays quantum signatures. Every dark absorption line and bright emission line in a stellar spectrum corresponds to particular transitions in atoms or molecules. Astronomers can identify elements in distant stars because hydrogen, sodium, calcium, and iron carry the same quantum fingerprints across the universe. A star may be so far away that its light has traveled for centuries or millions of years. Yet when that light is separated into a spectrum, the atom's private structure becomes visible. Quantum mechanics turns color into a message from remote matter. The spectral line is not infinitely sharp. Natural lifetime, thermal motion, pressure, magnetic fields, and other effects broaden or split it. The Zeeman effect separates energy levels in a magnetic field. The Stark effect does so in an electric field. Fine structure appears from relativistic corrections and spin-orbit interaction. Hyperfine structure emerges from coupling between electron and nuclear properties. Each refinement reveals another layer. The atom is not a tiny solar system. It is a resonant quantum architecture whose allowed transitions encode its environment. One of the most precise tests of quantum electrodynamics comes from the magnetic behavior of the electron. In a simple relativistic theory, the electron's magnetic moment has a particular value. Quantum fluctuations modify it slightly, producing the anomalous magnetic moment. The theoretical calculation includes contributions from increasingly complicated virtual processes, represented by Feynman diagrams. Experiment and theory agree to extraordinary precision. This success does not make the electron less mysterious. It makes the mystery exact. Quantum theory can predict how a single fundamental particle responds to a magnetic field with more accuracy than most measurements in science. Yet physicists still debate what the wave function means when no measurement is made. Precision and philosophical uncertainty coexist without canceling one another. The next step in the story begins when two quantum systems stop having independent descriptions. They become entangled. Entanglement is often described as a connection between distant particles, but the word connection can suggest the wrong picture. It is not a hidden wire, beam, or signal running through space. It is a property of the combined quantum state. The whole can be well defined even when the parts do not possess separate definite states of the same kind. Imagine two particles prepared so that their spins are opposite along any common axis that is measured. The total angular momentum can be fixed, while neither particle is assigned an independent spin direction before measurement. If one is measured and found spin up along a chosen axis, the other will be found spin down when measured along that same axis. Classically, one might explain this with a pair of gloves placed into separate boxes. Open one box in Paris and find a left glove. One instantly knows that the box in Tokyo contains the right glove. No influence traveled between the boxes. The properties were determined from the beginning. Quantum entanglement is stronger than the glove analogy. The experimenter can choose among different measurement axes after the particles have separated. The correlations across those choices follow a pattern that cannot be reproduced by any local theory, in which each particle simply carried a complete list of pre-written answers. Albert Einstein, Boris Podolsky, and Nathan Rosen brought the issue into sharp focus in 1935. Their argument began from two principles that seemed reasonable. First, if one can predict a physical quantity with certainty without disturbing a distant system, then that quantity should correspond to an element of reality. Second, physical influences should not travel instantaneously across space. Entangled states appeared to allow a choice of measurement on one particle to determine which property of the distant particle could be predicted. Einstein and his colleagues concluded that the quantum description must be incomplete. Perhaps particles possessed additional hidden variables that quantum mechanics failed to include. Einstein later referred to the situation as spooky action at a distance. He did not mean that experiments had already demonstrated a faster-than-light message. He meant that the quantum description seemed to conflict with his belief in a local, independently existing reality. For decades, the debate appeared philosophical. Quantum mechanics and a suitable hidden variable theory might make the same predictions in ordinary experiments. Then John Bell found a way to separate them. Bell was a physicist from Northern Ireland who worked at CERN and thought deeply about the foundations of quantum theory. In 1964, he derived inequalities that any local hidden variable model must satisfy. Quantum mechanics predicted that certain entangled correlations could violate those limits. This transformed the argument. The question was no longer only which picture felt more reasonable. Nature could be asked. John Clauser and collaborators performed early experimental tests with entangled photons. Alain Aspect and his colleagues later improved the tests, rapidly changing measurement settings while photons were in flight. Anton Zeilinger and many other researchers developed increasingly sophisticated sources, long-distance experiments, quantum teleportation, and tests closing important experimental loopholes. Again and again, the correlations followed quantum mechanics and violated Bell inequalities. The careful conclusion is not that one particle sends an ordinary message to another instantaneously. It is that the combination of locality and pre-existing hidden results cannot explain the observed statistics. Nature does not fit the classical picture in which separated objects carry complete local instruction sets determining every possible measurement outcome. Something in our ordinary idea of independent properties must give way. Bell experiments require many pairs. Each individual result looks random. Only after the records from both sides are compared does the non-classical correlation appear. This is why entanglement cannot be used to send a controllable signal faster than light. Suppose two observers, traditionally called Alice and Bob, share entangled particles. Alice chooses a measurement and obtains one of two outcomes. She cannot choose which result appears. Bob's local results also look random. Nothing in Bob's data alone reveals whether Alice measured, what axis she chose, or what result she received. The pattern emerges only when they later compare data through an ordinary communication channel limited by the speed of light. Quantum theory preserves the no-signaling rule even while violating local hidden variable expectations. This balance is one of its most subtle achievements. The correlations are stronger than classical local models permit, yet they do not create a practical telegraph to the past or across space instantaneously. Entanglement is also fragile. The particles need not be destroyed for the useful relationship to disappear. Uncontrolled interaction with the environment can spread the correlations into surrounding systems, producing decoherence. Maintaining entanglement requires isolation, careful control, and precise measurement. The phenomenon was once treated mainly as a philosophical puzzle. It is now a resource. Quantum teleportation is one of the clearest examples. The name suggests that matter vanishes in one place and reappears elsewhere, as in science fiction. The real process transfers a quantum state from one system to another using shared entanglement and classical communication. Alice and Bob first share an entangled pair. Alice also possesses a third particle in an unknown quantum state that she wants Bob's particle to acquire. She performs a joint measurement on her unknown state and her half of the entangled pair. That measurement destroys the original local state but produces a classical result. She sends that result to Bob by ordinary means. Depending on the message, Bob applies a corresponding operation, and his particle takes on the original state. No physical object has crossed the distance in the simple sense. No information has traveled faster than light. The quantum state has been reconstructed elsewhere through entanglement plus a classical message. The original cannot remain as an independent copy. This reflects the no-cloning theorem. In classical information, copying is easy. A bit that is definitely 0 or 1 can be read and duplicated. An arbitrary unknown quantum state cannot be copied perfectly. Any universal copying machine would have to preserve superpositions and inner products in a way forbidden by the linear structure of quantum mechanics. This limitation is not merely inconvenient. It enables forms of quantum security. In quantum key distribution, information is encoded in non-orthogonal quantum states, often states of single photons. An eavesdropper who does not know the preparation basis cannot measure each photon and reproduce it perfectly without introducing detectable disturbances. Alice and Bob can compare part of their data publicly to estimate whether the channel has been compromised. The security still depends on real devices being designed and implemented carefully. Detectors have imperfections. Sources may emit more than intended. Side channels can create vulnerabilities. Quantum cryptography does not make engineering irrelevant. But at its core, the protection can rest on physical laws rather than only on the assumed difficulty of a mathematical problem. Entanglement can also improve measurement. Quantum sensors use coherence, squeezing, or entanglement to reduce certain forms of noise and estimate time, fields, acceleration, or other quantities with exceptional sensitivity. Atomic clocks compare the phase evolution of quantum states. Interferometers measure tiny differences in path or energy. Magnetometers based on superconducting circuits or atomic spins can detect extraordinarily weak fields. The phrase quantum technology can sound futuristic, but the first quantum revolution already built much of the modern world. The second aims at controlling individual quantum systems and their entanglement deliberately, rather than relying mostly on the average behavior of enormous collections. Bell's theorem has a particularly beautiful role in this transition. A question raised by Einstein to challenge quantum mechanics became the foundation of new methods for communication, computation, and verification. Some quantum protocols use Bell violations to certify behavior without trusting every internal detail of a device. If observed correlations violate the appropriate inequality under well-controlled conditions, They can demonstrate that the data cannot have come from a purely local classical strategy. In principle, this enables device-independent forms of randomness generation and security. Quantum randomness itself can be treated as a resource. A measurement of a suitably prepared quantum state produces outcomes not predictable by any known hidden local variables. Devices can use such processes to generate random numbers for cryptography, simulation, and scientific sampling. The word random often suggests disorder, but quantum randomness can be exquisitely structured. Individual events are unpredictable, while their distributions and correlations obey exact mathematical laws. An entangled state may contain no definite value for either subsystem alone, yet a perfectly definite relation between them. This reversal is worth pausing over. Classical thinking begins with the parts and builds the whole. Quantum theory sometimes begins with the whole, while the parts acquire definite properties only in relation to a chosen measurement. That does not mean everything in the universe is usefully entangled with everything else in a way that can be exploited. Interactions do create widespread entanglement, but environmental decoherence makes most macroscopic correlations inaccessible. Useful entanglement is a carefully preserved pattern, not a mystical universal feeling. The language matters because quantum terms often escape the laboratory and acquire vague meanings. Entanglement does not explain telepathy. Observation does not mean positive thinking creates physical outcomes. Uncertainty is not a statement that all knowledge is unreliable. Quantum physics is strange, but its strangeness is disciplined by experiments and equations. The real phenomena are more interesting than the metaphors added to them. One of those real phenomena allows a particle to appear across a barrier that classical mechanics says it cannot cross. It is called tunneling, and without it the night sky would be dark. Quantum tunneling begins with the same wave-like spread that appeared in the double-slit experiment. A classical particle approaching an energy barrier behaves like a ball rolling toward a hill. If the ball has less energy than it needs to reach the top, it turns back. The region beyond the summit is inaccessible. A quantum particle is described by a wave function. When the wave reaches a barrier, it does not usually stop abruptly at the boundary. It penetrates into the classically forbidden region and decays with distance. If the barrier is thin enough, a small amplitude can remain on the far side. A measurement can then find the particle there. The particle has not borrowed energy in the casual sense sometimes used in popular explanations. Energy conservation remains part of the theory. The surprising feature is that a state with energy below the barrier can still have non-zero probability beyond it. The probability depends sensitively on barrier width, height, particle mass, and energy. A modest change can make tunneling vastly more or less likely. This exponential sensitivity turns the effect into both a natural clock and a technological tool. Radioactive alpha decay is one example. Inside certain unstable nuclei, an alpha particle can be thought of as confined by a potential barrier created by the strong nuclear force and electrical repulsion. Classically, it may not have enough energy to escape. Quantum mechanically, there is a small probability of tunneling through. For one nucleus, the moment of decay cannot be predicted. For a large collection, the half-life can be extremely stable. Some isotopes decay in fractions of a second. Others persist for billions of years. The barrier and the quantum state determine the scale. The same basic effect helps the sun shine. The sun's core is hot and dense, but the positively charged nuclei inside it repel one another electrically. Classical estimates once suggested that the protons did not have enough energy to overcome this Coulomb barrier often enough to sustain the observed fusion rate. Tunneling allows their wave functions to penetrate the barrier. On rare encounters, nuclei come close enough for the strong nuclear force to bind them and begin the chain of reactions that powers sunlight. Without tunneling, stars like the Sun would need very different conditions to fuse. The steady light crossing the room from a window during the day begins partly with quantum probability deep in a stellar core. Tunneling also allows instruments to see atoms. In a scanning tunneling microscope, an extremely sharp conducting tip is brought within a tiny distance of a conducting surface. A voltage is applied. Electrons tunnel through the vacuum gap, creating a current. Because tunneling probability changes exponentially with distance, a shift smaller than the width of an atom produces a measurable change in current. By moving the tip across the surface and adjusting its height to maintain a chosen current, the microscope maps atomic scale structure. The resulting image is not a conventional photograph. It is a reconstruction based on tunneling current and the electronic states of the surface. The sensitivity is so great that individual atoms can be resolved and, under suitable conditions, manipulated. Researchers have used scanning probes to move atoms one by one, constructing patterns that would be impossible to see without quantum mechanics and impossible to create with ordinary tools. A barrier that a classical particle should not cross becomes a ruler fine enough to map matter atom by atom. Tunneling appears in electronics as well. It enables tunnel diodes, influences the behavior of flash memory, and becomes a challenge when transistor features shrink. If insulating barriers become too thin, electrons can leak through them even when classical design says they should remain confined. Engineers must therefore work not only with the useful side of tunneling, but also with its refusal to respect ordinary barriers. Josephson junctions take tunneling into the macroscopic quantum world. Two superconductors separated by a thin insulating layer can support a supercurrent across the barrier. Cooper pairs tunnel coherently, and the current depends on the phase difference between the superconducting quantum states. This effect links voltage and frequency with extraordinary precision. Josephson junctions are used in electrical standards, highly sensitive magnetometers, and superconducting quantum circuits. The path from a particle leaking through a barrier to a national voltage standard is another example of quantum theory becoming infrastructure. To understand why particles and light interact so precisely, quantum mechanics had to be joined with special relativity. The result was quantum field theory. In the older particle picture, one imagines electrons and photons as objects moving through space. Quantum field theory reverses the emphasis. Fields are fundamental and extend throughout space. What we call a particle is a localized excitation of a field. The electron field is present everywhere. An electron is one quantum of excitation in that field. The electromagnetic field is also everywhere. A photon is one quantum of its excitation. Quark fields, neutrino fields, and other fields fill the universe in the same sense. This does not mean empty space is packed with a material substance like invisible fluid. Quantum fields are mathematical and physical structures whose excitations and interactions produce measurable events. They are the framework through which modern particle physics describes nature. Quantum electrodynamics, or QED, is the field theory of electrons, positrons, photons, and electromagnetic interaction. It was developed into a workable form in the 1940s by physicists including Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson. Earlier calculations ran into infinities. A charged particle interacts with the electromagnetic field, and naive attempts to include all possible quantum fluctuations produced divergent answers. Renormalization reorganized the theory so that measurable quantities could be expressed in terms of measured parameters, allowing finite predictions of astonishing precision. The process was initially controversial. Subtracting infinities can sound like hiding a problem, but renormalization became a deep and systematic part of quantum field theory. It also revealed that parameters such as charge and interaction strength depend on the scale at which they are probed. Feynman diagrams offered a visual language for calculations. Lines represent particles propagating, while vertices represent interactions. An electron can emit and absorb a photon. A photon can contribute through a temporary electron-positron pair. More complicated diagrams represent higher-order corrections. The diagrams are not necessarily literal films of tiny particles following every drawn route. They are terms in a mathematical expansion of possible processes. Yet they give physicists an intuitive way to organize an otherwise overwhelming calculation. At the lowest order, an interaction may look simple. At higher precision, the quantum fields allow every permitted intermediate contribution. The final result comes from adding amplitudes associated with all relevant possibilities. This logic is sometimes expressed through Feynman's path integral. To calculate an amplitude, one sums contributions from all possible histories connecting initial and final conditions. The classical path emerges because nearby histories tend to reinforce one another around stationary action, while wildly different phases often cancel. A thrown ball therefore appears to follow one smooth classical trajectory, not because quantum alternatives cease to exist, but because at large scales their phases interfere so that the classical path dominates with extraordinary sharpness. The path integral does not mean a visible object literally travels every imaginable route in the ordinary sense. It is a calculational framework assigning amplitudes to histories. Once again, the mathematical statement is precise while the everyday picture remains limited. The vacuum in quantum field theory is not simple nothingness. It is the lowest energy state of the fields. Even there, certain quantities fluctuate, and the vacuum can influence measurable systems. The phrase virtual particles often appears in descriptions of these effects. It is useful but easily misunderstood. Virtual particles are internal elements of perturbative calculations, not ordinary particles briefly popping into existence where they could be directly observed. They do not provide a loophole in energy conservation. The measurable predictions belong to the full quantum field, not to a cartoon of tiny objects appearing and disappearing at random. One measurable effect associated with the quantum vacuum is the Lamb shift. In the simplest relativistic treatment of hydrogen, certain energy levels should coincide. Precision measurements in the 1940s found a small difference. Quantum electrodynamics explained it through the interaction of the electron with fluctuations of the electromagnetic field and related radiative corrections. Another is the Casimir effect. Two uncharged conducting plates placed extremely close together in vacuum experience an attractive force. The boundaries alter the allowed modes of the electromagnetic field between and outside the plates. The resulting difference in quantum energy produces a force that can be measured. The Casimir effect is often described as proof that virtual particles press on the plates. The more careful explanation concerns quantum fields, boundary conditions, and changes in vacuum energy. Different calculational approaches can describe the same force without requiring one literal microscopic story. Even empty space becomes a physical state with structure. Yet the vacuum raises one of the greatest unresolved problems in physics. In cosmology, the universe's accelerated expansion is described by dark energy, often represented through a cosmological constant or vacuum like energy density. Straightforward estimates of quantum vacuum contributions disagree catastrophically with the observed scale. Depending on how the estimate is framed, the mismatch can be described as tens or even around 120 orders of magnitude. It is often called the worst theoretical prediction in physics. The exact comparison involves subtleties, but the central fact remains. Quantum field theory and cosmological observation do not yet fit together naturally on this point. The vacuum is at once one of the most accurately handled concepts in laboratory physics and one of the most mysterious in cosmology. Quantum electrodynamics became part of a larger structure. the standard model of particle physics. The standard model describes matter through quarks and leptons. There are 6 quark flavors: up, down, charm, strange, top, and bottom. There are 6 leptons: the electron, muon, tau, and 3 associated neutrinos. Each matter particle has an antiparticle with related properties and opposite charges where applicable. Quarks combine to form protons, neutrons, and many other composite particles. A proton contains 2 up quarks and 1 down quark as valence quarks, embedded in a dynamic sea of gluons and quark-antiquark activity. A neutron contains 1 up and 2 down valence quarks. The strong interaction is described by quantum chromodynamics. Quarks carry a property called color charge, unrelated to visual color. Gluons carry the strong force and also interact with one another because they themselves carry color. This self-interaction produces unusual behavior. At very short distances and high energies, quarks interact more weakly, a property called asymptotic freedom. At larger distances, the force does not fade in the simple way of electromagnetism. Quarks are confined inside composite particles and are not normally observed in isolation. Most of the mass of a proton or neutron does not come directly from the bare masses of its quarks. It arises from the energy of the strongly interacting quark and gluon fields inside. Through Einstein's relation between mass and energy, the dynamics of quantum chromodynamics create most of the mass in ordinary atomic nuclei. The visible world is heavy largely because confined quantum fields are active. The weak interaction allows certain kinds of particle transformation and radioactive decay. It is carried by the W and Z bosons. The electromagnetic and weak interactions are united at high energies in the electroweak theory. That unification requires a mechanism through which some elementary particles acquire mass, while the photon remains massless. The Higgs field fills space, and particles interact with it to different degrees. The associated excitation is the Higgs boson. The Higgs mechanism is often compared to moving through a crowd, with some particles slowed more than others. The metaphor can be useful but incomplete. The field does not produce drag in the ordinary sense. A particle moving freely through the Higgs field does not continuously lose energy. Its interaction changes the relation between energy and momentum, appearing as mass. In July 2012, the ATLAS and CMS collaborations at CERN announced the discovery of a new particle near a mass of 125 gigaelectronvolts. Further measurements established that its properties were consistent with the Higgs boson predicted by the Standard Model. The discovery required collisions at the Large Hadron Collider, enormous detectors, international teams, and analysis of vast numbers of events. The Higgs itself decays almost immediately. Physicists reconstructed it from patterns among the particles produced in its decay. A field filling all of space was revealed not by catching a durable Higgs particle in a container, but by creating fleeting excitations and reading their debris. The Standard Model is extraordinarily successful, but it is not complete. It does not include a quantum theory of gravity. It does not identify the dark matter inferred from galaxies and cosmology. It does not explain why the universe contains far more matter than antimatter. Its neutrinos require extensions because they have mass, while the minimal original formulation treated them as massless. Neutrinos provide their own quiet quantum journey. They interact so weakly that trillions produced by the sun pass through the human body every second without notice. For decades, experiments detected fewer solar neutrinos than models predicted. The resolution was not that the sun was failing, but that neutrinos change flavor as they travel. Electron, muon, and tau neutrinos are not identical to states of definite mass. Each flavor is a quantum superposition of mass states. As the components evolve with slightly different phases, The probability of detecting one flavor changes with distance and energy. A neutrino born as one type can later appear as another. Neutrino oscillation is quantum interference stretched across kilometers through Earth, atmosphere, reactors, and sunlight. Because oscillation requires differences in mass, it revealed physics beyond the simplest standard model. The masses are tiny, and their full origin remains unknown. Quantum physics is not a finished cabinet of answers. It is a framework so successful that its remaining gaps become sharply visible. Before moving toward the largest unanswered questions, it is worth returning to the room and asking how a theory born from furnaces, spectral lines, and thought experiments became part of ordinary life. The answer does not begin with a futuristic machine. It begins with a small piece of germanium on a laboratory bench. By the middle of the 20th century, telephone networks and early electronic machines depended heavily on vacuum tubes. Tubes could amplify and switch electrical signals, but they were bulky, hot, fragile, and hungry for power. Bell Laboratories wanted something smaller and more reliable. The hope was that a solid material might control current without requiring electrons to travel through an evacuated glass bulb. The challenge was that solids are not simply collections of tiny wires. Inside a crystal, electrons occupy quantum states shaped by the repeating arrangement of atoms. When many atoms come together, their individual energy levels broaden into bands. Some bands are filled, others are empty. Between them may lie gaps containing no allowed electron states. Those gaps decide how the material behaves. In a metal, electrons have accessible states that let them respond easily to an electric field. In an insulator, a large gap blocks ordinary conduction. A semiconductor occupies the useful middle ground. Its conductivity can be altered by temperature, light, electric fields, and the deliberate addition of small amounts of other elements. In December 1947, John Bardeen and Walter Brattain were working with a sliver of germanium and two closely spaced metal contacts. Their device was not elegant by modern standards. It looked more like a delicate laboratory arrangement than the ancestor of a computer chip. Yet when they adjusted the contacts and applied a signal, the output became stronger. The solid crystal had amplified electricity. A few days later, they demonstrated the effect to colleagues at Bell Labs. William Shockley, who had helped organize the semiconductor research program, soon developed the theory and design of the junction transistor. The three physicists later shared the Nobel Prize for Research on Semiconductors and the discovery of the transistor effect. The historical photograph of the first device can seem almost modest. There is no glowing screen, no polished metal cabinet, and no obvious sign that the world has changed. But the transistor did something profound. It turned the quantum energy structure of a crystal into a controllable switch. The control became possible through carefully prepared regions of semiconductor. Add atoms that contribute extra mobile electrons, and the material becomes N-type. Add atoms that leave effective vacancies, called holes, and it becomes P-type. At the boundaries between these regions, electric fields and quantum band structure determine whether charges can pass. A modern field effect transistor uses a voltage at one terminal to reshape a conducting channel. In one condition, current can flow. In another, it is suppressed. The states are stable enough to represent the zeros and ones of digital logic. Connect transistors into gates, gates into circuits, and circuits into layers, and a piece of silicon can store memories, process images, decode sound, and carry a voice through the night. The journey from the first germanium device to billions of microscopic switches required decades of chemistry, lithography, crystal growth, materials science, and manufacturing. Quantum mechanics did not automatically hand engineers a finished computer. It gave them the rules of the material. Human ingenuity learned how to shape those rules into architecture. As transistors became smaller, the hidden quantum foundation became increasingly visible. An electron can tunnel through an insulating layer that would have blocked it in a larger device. Confinement changes the allowed energies. A variation involving only a few atoms can alter a current. The technology built from quantum mechanics now operates near scales where quantum effects are not only useful, but also obstacles that must be controlled. Light-emitting diodes tell the same story in reverse. In a semiconductor, an electron can lose energy by recombining with a hole. The energy may leave as a photon. The size of the band gap helps determine the photon's frequency and therefore its color. By changing the crystal composition, engineers create red, green, blue, infrared, and ultraviolet light. A white LED often begins with a blue or ultraviolet semiconductor source. A phosphor absorbs part of that light and re-emits a broader mixture of colors. What looks like simple household illumination is a carefully arranged sequence of quantum transitions. A solar cell reverses part of the exchange. A photon from the sun enters a semiconductor and can lift an electron into a mobile state, leaving a hole behind. Internal electric fields guide the two charge carriers in opposite directions, creating current. The puzzle that once led Einstein to the light quantum now helps rooftops and satellites turn sunlight into electricity. A digital camera performs the same conversion millions of times across an array. Photons reach individual pixels and create charges in a semiconductor. The number of collected electrons becomes a brightness value. Color filters and computation rebuild the scene. A photograph that seems continuous is assembled from localized exchanges of light and matter. Then there is the laser, perhaps the most graceful device to emerge from quantum theory. Einstein predicted stimulated emission in 1917. An excited atom can release a photon spontaneously, but it can also be prompted by an incoming photon of the right energy. The emitted photon matches the first in frequency, phase, polarization, and direction. One orderly wave of light encourages another. For decades, the idea remained a principle waiting for suitable materials and engineering. In 1960, Theodore Maiman produced the first working laser using a synthetic ruby crystal. A flash lamp excited atoms in the ruby. Mirrors sent light repeatedly through the crystal, and a carefully chosen portion emerged as a narrow red beam. The beam was unusual because its photons behaved collectively. Their phases were related, their direction was concentrated, and their frequency range was narrow. This coherence allowed laser light to be focused, timed, and compared with the precision ordinary lamps could not provide. Lasers now scan barcodes, cut metal, guide surgery, read surfaces, cool atoms, measure the moon, transmit messages through optical fiber, and help gravitational wave observatories detect changes in distance smaller than an atomic nucleus. The same principle appears in a supermarket checkout and in some of the most sensitive experiments ever built. Much of the global internet travels as laser pulses through glass. The fiber guides light by its refractive structure, while repeaters, amplifiers, detectors, and timing systems preserve the information over enormous distances. The words reaching you may have crossed part of their journey as organized photons in a strand of glass thinner than a finger. Atomic clocks use quantum regularity in a different way. A mechanical clock counts swings. A quartz clock counts vibrations in a crystal. An atomic clock tunes microwaves or laser light to a transition between two quantum energy levels. Imagine a quiet laboratory containing a cloud of cesium atoms. The atoms are prepared, cooled, and exposed to microwave radiation. When the frequency is slightly wrong, relatively few atoms change state. As the frequency approaches resonance, the transition probability rises. Electronics use that response to correct the oscillator again and again. The official second is defined through a particular transition in cesium-133. Optical clocks use much higher frequency transitions in atoms or ions such as strontium, ytterbium, mercury, and aluminum. Because the frequency is higher, the clock has more oscillations to divide and compare, allowing extraordinary precision. The clock does not rely on one atom acting like a tiny pendulum. It relies on identical quantum systems responding to the same carefully defined frequency. The repeated transition becomes a ruler for time. Global navigation depends on such rulers. Satellites broadcast synchronized signals. A receiver compares their arrival times and calculates its distance from several satellites. A tiny timing error becomes a substantial error in position. General relativity must also be included because clocks in orbit move differently and sit in a different gravitational field from clocks on Earth. Quantum transitions and curved spacetime cooperate whenever a navigation device finds a street. Modern clocks are so sensitive that a small change in height can produce a measurable difference in ticking rate because gravity affects time. A device developed to keep time becomes a probe of elevation, Earth's gravitational field, and perhaps one day subtle geological change. Medicine uses other quantum signals. Magnetic resonance imaging detects the response of nuclear spins, especially hydrogen nuclei abundant in water and fat. Positron emission tomography follows a radioactive tracer that emits positrons. When a positron encounters an electron, the pair annihilates into photons that detectors use to reconstruct where the event occurred. The result is a human image assembled from spin, antimatter, quantum transitions, and probability. None of these technologies looks like the double-slit experiment while operating. Yet all of them grew from the same decision to trust a theory that initially seemed too strange to describe reality. Superconductivity reveals quantum behavior on a scale large enough to carry currents through wires. In an ordinary conductor, electrons scatter from lattice vibrations, impurities, and imperfections, producing resistance and heat. In a conventional superconductor cooled below a critical temperature, electrons near the Fermi surface form Cooper pairs through an effective attraction mediated by vibrations of the crystal lattice. Two electrons repel electrically, so pairing sounds unlikely. The attraction is subtle and collective. One electron slightly distorts the positively charged lattice. That distortion can influence another electron. Under the right low-temperature conditions, the effective interaction allows paired states. Cooper pairs behave collectively as bosonic entities and condense into a coherent quantum state separated from many ordinary excitations by an energy gap. Scattering that would resist individual electrons cannot easily disrupt the collective flow without breaking pairs or creating excitations. The result is electrical current with zero direct current resistance under appropriate conditions. A persistent current can circulate for extraordinarily long times in a superconducting ring. Superconductors also expel magnetic fields from their interiors when entering the superconducting state, a phenomenon called the Meissner effect. This is deeper than simply perfect conductivity. It shows that superconductivity is a distinct thermodynamic quantum phase. Type II superconductors allow magnetic flux to enter in quantized vortices above a lower critical field. Pinning those vortices can help stabilize levitating magnets. Demonstrations of a magnet floating above a cooled superconductor look like stage magic, but the effect arises from quantum coherence, magnetic flux quantization, and material defects. Superconducting magnets are used in MRI machines and particle accelerators. Superconducting circuits also form one of the leading platforms for quantum computing. Josephson junctions provide nonlinear quantum elements that can behave as artificial atoms with controllable energy levels. Not all superconductors fit the simplest conventional picture. Copper oxide materials can superconduct at temperatures much higher than traditional metallic superconductors, though still usually far below room temperature. Iron-based and other unconventional superconductors add further families. The mechanisms behind high-temperature superconductivity remain an active field of research. A phenomenon discovered more than a century ago still contains unsolved questions. Superfluidity is a related macroscopic quantum effect. Certain liquids cooled to very low temperatures can flow with extremely low viscosity. Helium-4 becomes superfluid and displays remarkable behavior. It can climb thin films along container walls, flow through tiny openings, and support quantized vortices. Helium-3, made of fermionic atoms, becomes superfluid only at much lower temperatures through pairing, somewhat analogous to electron pairing in superconductors. Its phases have complex internal structure and have become laboratories for studying quantum order. Bose-Einstein condensation offers one of the most beautiful examples of a prediction waiting patiently for the world to invent the tools required to see it. In the early 1920s, Satyendranath Bose found a new way to count the possible states of light particles. He sent his work to Einstein, who recognized its importance, helped bring it to publication, and extended the method from photons to atoms. The mathematics suggested that a gas of suitable particles, cooled close enough to absolute zero, would undergo a remarkable change. A large fraction of the atoms would gather into the same lowest energy quantum state. The predictions sounded clear on paper and almost unreachable in a laboratory. Ordinary gases remain far too warm. Their atoms move too rapidly, their matter waves remain too short, and collisions with the environment destroy delicate coherence. The required temperature was not merely cold in the everyday sense. It was billions of times closer to absolute zero than a winter night. For roughly 70 years, the condensate remained an idea. Then several technologies matured together. Tuned laser beams could slow atoms by transferring photon momentum against their motion. Magnetic fields could hold the atoms away from warm container walls. Evaporative cooling could remove the fastest atoms, allowing the remainder to settle into an even colder distribution. The procedure resembles cooling a cup by allowing the hottest molecules to escape, except that the cup is an invisible magnetic trap and the remaining cloud contains atoms moving only fractions of ordinary thermal speeds. Every stray collision, vibration, and magnetic fluctuation matters. The experiment is less like placing something in a freezer than like persuading motion itself to become quiet. In 1995, teams in Boulder and at MIT created Bose-Einstein condensates in dilute gases of rubidium and sodium. The first images did not show a glowing new substance. They showed distributions of atoms after the trap was released. As the temperature crossed a critical point, a narrow central peak appeared within the broader cloud. Many atoms had entered the same quantum state. At those temperatures, the de Broglie wavelengths of the atoms overlap. The gas can no longer be understood only as distinguishable particles following separate routes. A macroscopic fraction behaves coherently, described by a shared wave function. Release two condensates and let them overlap, and matter can form interference fringes. Rotate one, and vortices appear only in quantized units. Guide atoms out of the condensate, and the resulting coherent matter wave can be compared, carefully, with a laser beam made from light. The cloud remains fragile. A small amount of heat can destroy the condensate. Yet while it lasts, quantum behavior that is normally confined to microscopic systems becomes visible across a laboratory image. An equation written in the 1920s becomes a cloud one can point to. The quantum Hall effect reveals a different kind of macroscopic order. Confine electrons to an almost two-dimensional layer, cool them, and apply a strong magnetic field. Instead of changing smoothly, the transverse electrical conductance forms precise plateaus set by fundamental constants. At first, the system appears to be only a sheet containing many interacting electrons. Under the right conditions, however, the collective state becomes more exact than the imperfections in the material. Disorder that might have blurred an ordinary measurement helps stabilize the plateaus. A complicated piece of matter produces a universal number. In the fractional quantum Hall effect, interactions organize electrons into states whose excitations behave as though they carry fractions of the electron's charge. These quasiparticles are not new fundamental particles traveling through empty space. They are patterns made real by the coordinated behavior of the entire system. Condensed matter physics is filled with such entities. A phonon is a quantum of collective vibration in a crystal. A magnon is a quantum of a spin wave. An exciton is a bound state of an electron and a hole. Under special conditions, theorists expect anyons whose exchange behavior lies between the familiar categories of fermions and bosons. The lesson is that quantum physics does not merely provide a list of elementary ingredients. When enormous numbers of particles interact, they can create new phases, new effective particles, and new rules that do not appear in the isolated components. This makes many-body quantum systems difficult to calculate. The state space grows rapidly with every additional particle. Even when the basic equation is known, predicting what a material will do may overwhelm a classical computer. Researchers therefore build controlled quantum systems that imitate less accessible ones. Ultra-cold atoms arranged in patterns of laser light can model particles in a crystal. Trapped ions can reproduce networks of interacting spins. Superconducting circuits can imitate fields and phase transitions. Rather than forcing a classical machine to store every quantum amplitude, the experiment allows one quantum system to explore the behavior of another. Nature becomes a calculator for nature, and that idea opens the door to the quantum computer. Walk into a quantum computing laboratory, and the first impression may not be futuristic. There are cables, oscilloscopes, vacuum pumps, laser tables, microwave generators, and computers displaying ordinary graphs. In some laboratories, the most prominent object is a dilution refrigerator, a tall metal structure surrounding nested shields and stages that descend toward temperatures only a small fraction of a degree above absolute zero. The machine looks large because the quantum object inside is delicate. A classical bit is engineered to occupy one of two stable conditions, labeled 0 and 1. A quantum bit, or qubit, also has two basis states, but its full state can be a superposition described by complex amplitudes. Those amplitudes contain both magnitude and phase. When the qubit is measured, the result is 0 or 1, yet before measurement the phase affects how later operations interfere. That phase is the essential part. A qubit is not a tiny classical switch secretly holding both answers. If it were, quantum computing would offer little new. A sequence of quantum gates rotates amplitudes, creates entanglement, and arranges interference so that some possible outcomes grow while others fade. The double-slit experiment has returned, disguised as computation. With one qubit, the geometry can be pictured as a point on a sphere. With two qubits, the combined state can involve 4 basis configurations. With 3, 8. In general, n qubits require 2 to the power n amplitudes to describe an arbitrary pure state. That exponential growth is why quantum systems are difficult to simulate classically. It is also why the usual popular explanation can be misleading. A quantum computer does not simply try every answer in separate parallel worlds and then print the correct one. Measurement reveals only one result. The algorithm must arrange the state so that the desired structure is concentrated into outcomes that can actually be read. The calculation is closer to composing waves than checking a list. Paths through the computation acquire phases. Some reinforce, others cancel. A successful algorithm turns an abstract property of the problem into an interference pattern in the final measurement statistics. Richard Feynman arrived at the idea from a practical frustration. Nature is quantum, but a classical computer attempting to simulate many interacting quantum particles must track a state space that grows exponentially. Feynman suggested that perhaps the right simulator would be a machine governed by the same quantum rules as the system being studied. This remains one of the most convincing reasons to build quantum computers. Molecules, catalysts, magnetic materials, and chemical reactions involve interacting electrons and nuclei. Classical methods provide powerful approximations, but some states are extraordinarily difficult to represent. A controlled quantum processor may eventually model selected systems more naturally. The word eventually matters because keeping a qubit coherent is difficult. A qubit must be isolated from unwanted noise, yet connected strongly enough to be initialized, controlled, entangled, and measured. It must ignore the environment until the experimenter asks it to respond. Every platform solves this contradiction differently. In a superconducting processor, the qubit is an electrical circuit interrupted by one or more Josephson junctions. The junction makes the circuit's energy levels uneven, allowing two of them to serve as the computational states. Microwave pulses rotate the state. Coupling elements entangle neighboring circuits. The entire chip is cooled deeply so that thermal excitations do not overwhelm the quantum levels. The refrigerator does not cool the qubit merely for comfort. At ordinary temperature, the surrounding energy would be enormous compared with the spacing between the states. The qubit would be continually disturbed. Near absolute zero, the thermal background becomes quiet enough for control. A trapped ion computer uses a different kind of qubit, an individual charged atom held above electrodes or inside electromagnetic fields. Internal atomic states store information. Lasers perform rotations, and shared vibrational motion helps entangle the ions. Because atoms of the same isotope are naturally identical, their quantum transitions can be remarkably stable. Neutral atom systems arrange uncharged atoms in arrays of focused laser traps called optical tweezers. Exciting an atom to a large Rydberg state creates strong interactions that can mediate entangling operations. Photonic systems encode quantum information in polarization, path, or arrival time. Semiconductor devices confine individual electrons and use their spins. Other approaches search for topological states whose information would be stored in global patterns less sensitive to local disturbances. Each platform is a different answer to the same question. How can a quantum state remain private from the environment while still obeying precise commands? No platform has removed every difficulty. Some offer fast gates but shorter coherence. Some preserve states beautifully but are harder to connect in large numbers. Some are fabricated like chips. Others require elaborate lasers and vacuum systems. Quantum engineering is not waiting for one obvious winner. It is exploring several physical languages. Noise appears in many forms. A qubit can exchange energy with its surroundings. Its phase can drift. A control pulse can be slightly too strong. A measurement can misidentify the state. Crosstalk can make one operation disturb a neighbor. The system can even leave the two selected energy levels and leak into states that were not meant to participate. Classical computers also suffer errors, but they can copy information freely and use redundancy. An unknown quantum state cannot be copied perfectly because of the no-cloning theorem. Measuring it directly generally changes it. For a time, these restrictions made error correction seem impossible. The solution was to stop storing the information in any one physical qubit. A logical qubit can be distributed across an entangled pattern of many physical qubits. Carefully chosen measurements do not reveal the logical value. Instead, they reveal error syndromes, clues showing whether the pattern has been disturbed in particular ways. Imagine a message woven into relationships rather than written on one thread. A local tear changes nearby relationships and can be detected without reading the message itself. If errors remain sparse and corrections happen quickly enough, the logical state survives. Quantum error-correcting codes turn a continuum of small physical mistakes into discrete patterns that classical electronics can diagnose. The surface code, for example, arranges qubits in a lattice and repeatedly checks local parity relations. If the physical error rate is below a threshold, making the code larger can reduce the logical error dramatically. The price is overhead. One reliable logical qubit may require many physical qubits, continual measurements, rapid classical processing, and precise calibration. This is why a headline announcing a raw qubit count says less than it appears to. Fidelity, connectivity, coherence, measurement quality, and logical error rate determine what the machine can actually do. The long-term goal is fault tolerance. Computation that can continue even while individual components make occasional mistakes. The phrase does not mean a perfect machine. It means a machine whose logical errors can be suppressed by adding and managing redundancy. Why undertake such an elaborate effort? Peter Shor provided one dramatic answer in 1994. He discovered a quantum algorithm that could factor large integers efficiently on a sufficiently powerful fault-tolerant quantum computer. The algorithm does not test divisors one by one. It converts the problem into finding a hidden period, uses quantum interference and a quantum Fourier transform to expose that structure, and then uses classical mathematics to recover the factors. Widely used public key cryptographic systems have relied on problems related to factoring or discrete logarithms being difficult for classical computers. A large fault-tolerant quantum computer would threaten several of those systems. Such a machine does not yet exist at the necessary scale, but the risk has already changed cryptography. Post-quantum algorithms are being deployed so that information can remain secure even if large quantum computers arrive later. The transition matters because encrypted data can be collected now and stored for future attack. A theoretical quantum algorithm therefore influences security decisions decades before the hardware is ready. Grover's search algorithm offers a different advantage. For an unstructured search among many possibilities, it reduces the required number of queries from roughly the total number to roughly its square root. The improvement is substantial but not unlimited, and classical systems can often compensate by increasing key sizes or using parallel hardware. Other quantum algorithms target simulation, sampling, optimization, linear algebra, and selected differential equations. Some provide mathematically proven advantages under clear assumptions. Others remain proposals whose real benefit may disappear after accounting for data loading, error correction, or improved classical methods. This uncertainty is healthy. Quantum computing is neither a universal miracle nor an empty illusion. It is a specialized form of computation that may become powerful for certain structures and remain unnecessary for most ordinary tasks. A future quantum computer will still need classical machines. Classical processors create control pulses, compile circuits, decode error syndromes, interpret measurements, and manage databases, screens, and networks. The quantum processor will be a partner or accelerator, not a replacement for every laptop and server. The development may be gradual. Early classical computers filled rooms and solved narrow problems. Their transformation into ordinary infrastructure required improvements in components, manufacturing, programming, memory, networking, and reliability. Quantum computing may follow its own slower and more specialized path. Even before large fault-tolerant machines exist, the experiments are scientifically remarkable. Physicists can prepare individual atoms, control artificial atoms and circuits, generate entangled photons, and perform sequences of operations on states that earlier generations could discuss only in thought experiments. The cat, the entangled pair, and the coherent superposition have become engineering specifications. Quantum networks extend the challenge beyond one processor. Photons can carry quantum states through fiber or free space because they travel rapidly and interact weakly. Matter qubits can serve as memories because they can remain in one place and be controlled. A useful network must connect the two. An ordinary optical repeater receives a faint classical signal, reads it, amplifies it, and sends a new copy. A general unknown quantum state cannot be copied that way. Quantum repeaters instead aim to create entanglement across shorter links, store it, and extend it through entanglement swapping and error management. Experiments have distributed entanglement through optical fiber, open air, and satellite links. The distances demonstrate the principle, but a practical network still needs efficient sources, reliable memories, low-loss interfaces, synchronization, and correction. The phrase quantum internet can refer to several stages. The earliest networks may distribute cryptographic keys. More advanced systems could connect clocks and sensors, allowing them to compare phase with enhanced precision. A mature network might teleport quantum states between processors and support distributed computation. Classical communication remains necessary at every level. Quantum teleportation needs a classical message. Entanglement cannot reveal a distant choice by itself. The quantum layer adds new correlations and new guarantees. It does not replace the speed limit set by relativity. Quantum information theory makes these restrictions precise. The Holivo bound limits how much classical information can be extracted from quantum states. The no cloning and no broadcasting theorems restrict copying. Monogamy limits how strongly one system can share entanglement with several others. Information disturbance relations connect knowledge with the changes required to obtain it. Superdense coding and teleportation reveal a carefully balanced exchange. With prior entanglement, sending one qubit can communicate two classical bits in superdense coding. Teleporting one unknown qubit consumes shared entanglement and requires two classical bits. The resources transform into one another according to exact rules. The laws permit remarkable things, but they do not permit everything. A quantum computer cannot read infinitely many numbers from one qubit. A network cannot signal faster than light. Teleportation cannot leave an independent perfect copy behind. Vacuum fluctuations cannot be wired into an unlimited source of free energy. Consciousness does not gain a special switch for selecting reality. The actual theory is more disciplined and more interesting than the science fiction built around it. It allows possibilities to interfere, information to be shared non-classically, and computation to follow paths unavailable to ordinary bits. At the same time, it places exact limits around every advantage. Those limits lead naturally to the edge where quantum theory meets its greatest unfinished problem, gravity. Quantum mechanics and general relativity are both extraordinarily successful, but they describe the world through different structures. Quantum theory treats fields and probabilities against a space-time framework. General relativity makes space-time itself dynamic, curved by matter and energy. In most situations, one theory can be used while quantum effects of gravity are neglected. At the surface of Earth, gravity is weak enough that quantum field theory works against an approximately fixed spacetime. In planetary and stellar motion, general relativity works while the quantum details of matter can often be summarized. But some places demand both. Near the center of a black hole, according to classical relativity, curvature can become extreme. In the earliest moments of the universe, matter and space-time reached energies and densities where quantum gravitational effects should matter. A complete theory must explain space-time and quantum fields together without producing contradictions or uncontrollable infinities. Several approaches attempt this. String theory replaces point-like, fundamental particles with tiny one-dimensional strings whose different vibrational modes appear as different particles. One mode behaves like a graviton, the hypothetical quantum of gravity. The theory naturally includes gravity and has produced deep connections among geometry, quantum field theory, black holes, and mathematics. But string theory typically requires additional spatial dimensions and possesses a vast landscape of possible solutions. Direct experimental evidence at the relevant scale remains absent. It is a rich framework rather than a confirmed final theory. Loop quantum gravity takes a different route, seeking to quantize geometry itself. Areas and volumes acquire discrete spectra, and spacetime is described through networks of quantum relations. The approach does not begin by unifying all forces in the same way as string theory, but focuses on building quantum spacetime from the principles of general relativity. Other programs include causal dynamical triangulations, asymptotic safety, group field theory, emergent gravity, and approaches based on quantum information. No single framework has been established experimentally as the correct theory. The problem is difficult partly because the natural scale of quantum gravity is extraordinarily remote. Planck length is around 10 to the power of minus 35 meters, far smaller than the distances directly probed in laboratories. The energies needed to examine that scale straightforwardly are beyond any conceivable accelerator. Nature may still provide indirect clues through black holes, cosmology, gravitational waves, high-energy particles, or subtle violations of known symmetries. But the evidence is sparse, and theory must navigate many possibilities. Black holes bring the conflict into one sharp paradox. Stephen Hawking showed that quantum fields around a black hole horizon predict thermal radiation. The black hole slowly loses energy and can eventually evaporate. The radiation appears almost featureless, characterized mainly by temperature. If a black hole forms from matter in a definite quantum state and evaporates into purely thermal radiation, what happens to the information describing the original state? Ordinary quantum evolution preserves information in the sense that a pure state evolves unitarily into another pure state. Complete loss would violate that structure. This is the black hole information paradox. Proposed resolutions include information encoded in subtle correlations within the Hawking radiation, remnants, modifications near the horizon, holographic descriptions, and ideas in which spacetime geometry emerges from entanglement. Developments in quantum gravity and quantum information have deepened the discussion, but a universally accepted physical account remains under debate. The paradox suggests that information, gravity, and spacetime may be more intimately related than the older theories reveal. The holographic principle is one striking possibility. It proposes that the information describing a region of space may be encoded on a lower dimensional boundary, somewhat as a hologram stores a three-dimensional image on a surface. In certain mathematical settings, a gravitational theory in one space can be equivalent to a non-gravitational quantum field theory on its boundary. This does not mean the everyday universe is a simple projection on a wall. It means that dimension and locality may emerge differently in quantum gravity than familiar geometry suggests. Entanglement may help build spacetime. In some theoretical models, changing patterns of entanglement changes the connectedness of the emergent geometry. The same phenomenon that puzzled Einstein as spooky correlation could be part of the structure from which spatial relationships arise. The proposal remains theoretical, but it creates a remarkable circle. Quantum mechanics once seemed strange because it allowed correlations across space. Quantum gravity may reveal that space itself depends on quantum correlation. The founders of quantum mechanics sensed these deeper questions even before the modern language of information existed. At the Solvay conferences of 1927 and 1930, Many of the physicists who had built the new theory gathered in the same rooms. Einstein challenged Bohr with thought experiments designed to restore simultaneous reality to quantities quantum mechanics treated as incompatible. Bohr responded, sometimes after sleepless analysis, by showing how the measuring apparatus itself had to be included and how the proposed experiment could not escape quantum limits. The debates are often told as a contest with a winner. The truth is more interesting. Bohr defended the consistency of quantum mechanics, and the theory survived every challenge. Einstein kept insisting that its conceptual cost should not be ignored. His objections helped sharpen the questions that later led to entanglement experiments and Bell's theorem. A critic of quantum mechanics helped reveal one of its deepest truths. Einstein was not simply an old physicist refusing new ideas. He had helped launch the quantum revolution with the light quantum. He understood the theory's power intimately. His discomfort came from taking its implications seriously. Bohr also resisted simple slogans. His principle of complementarity argued that experimental arrangements revealing wave-like behavior and those revealing particle-like information are mutually exclusive, yet jointly necessary for a complete account of quantum phenomena. The system cannot be assigned every classical attribute at once independent of the context in which it is measured. Complementarity does not mean truth changes according to opinion. It means that physical questions are defined through arrangements that may be incompatible with one another. An apparatus designed to preserve interference does not also produce a definite path record. An apparatus designed to reveal the path changes the conditions required for interference. Later experiments made these choices increasingly subtle. In delayed choice experiments, the decision about which kind of measurement to perform can be made after a quantum system has entered an interferometer. The results still fit quantum mechanics. It can sound as though a choice in the present changes what the particle did in the past. The safer conclusion is that the experiment does not support a simple classical history in which the particle had already committed to being a wave or a particle. Quantum theory predicts correlations among preparation, apparatus, and final measurement without requiring one definite classical story between them. Quantum eraser experiments are similarly easy to exaggerate. Path information can be encoded in another system, destroying visible interference in the unsorted data. If later measurements group the events according to complementary information, interference-like and anti-interference patterns can appear in the correlated subsets. The total pattern remains without interference, and no message travels backward in time. These experiments do not rewrite recorded history. They reveal that quantum correlations cannot always be compressed into one ordinary narrative about what happened between source and detector. The desire for a narrative is deeply human. A ball leaves a hand, follows a path, and lands. A planet circles a star. A sound wave moves through air. Classical physics gives events a continuous story even when no one watches. Quantum mechanics gives a state, a law of evolution, a set of possible measurements, and probabilities of outcomes. Whether there is one deeper story underneath depends on interpretation. Perhaps the wave function is physically real and branches into worlds. Perhaps particles have definite positions guided non-locally. Perhaps collapse is an objective process. Perhaps quantum states are relational or informational. Perhaps a future theory will place all these views in a wider framework. Experiments can sometimes distinguish modified theories from standard quantum mechanics. They can test objective collapse models, search for new nonlinearities, and extend superposition to larger masses and longer times. But several interpretations reproduce the same known predictions exactly, making them difficult or impossible to separate by ordinary experiments. This does not make interpretation meaningless. A picture influences which questions seem natural, which new theories are attempted, and how concepts from information, gravity, or cosmology are connected. Yet humility is necessary. Agreement with existing data belongs to the mathematics shared by the interpretations, not automatically to one preferred story. Quantum physics teaches humility in another way. The theory is famously strange to intuition, but intuition is not a fixed property of the mind. It is trained by experience. A child growing up near the sea learns to anticipate waves. A musician feels resonance without solving equations. An engineer develops intuition for circuits. Human beings lack direct experience of isolated electrons and coherent superpositions, so quantum behavior initially feels impossible. With repeated study, some aspects become familiar, though never identical to everyday motion. Physicists learn to think in state spaces, operators, symmetries, amplitudes, and conservation laws. They develop a quantum intuition that is mathematical rather than visual. The theory does not become ordinary, but it becomes navigable. There is no shame in failing to picture a wave function in a space with millions of dimensions. The mathematics was developed precisely because ordinary pictures were insufficient. The phrase "no one understands quantum mechanics" is often repeated. It captures genuine conceptual unease, but it can also mislead. Physicists understand how to use quantum mechanics with extraordinary depth. They design experiments, calculate spectra, build lasers, predict particle collisions, and control individual atoms. What remains disputed is not whether the theory works, but how its mathematical structure should be translated into one final picture of reality. Understanding has layers. One can understand how to calculate. One can understand which experiments support the theory. One can understand why classical analogies fail. And one can still remain uncertain about what the deepest ontology is. Science is not weakened by admitting those layers. It becomes more honest. The quiet wonders of quantum physics are therefore not only the dramatic ones. Entanglement and superposition attract attention, but equally wonderful is the stability of a glass of water. The oxygen atom keeps its characteristic structure. The electrons in neighboring molecules obey exclusion. Photons interact with vibrational modes. Hydrogen bonds shape the liquid. Thermal motion jostles everything without dissolving the quantum foundations beneath it. A glass looks classical because an enormous number of quantum systems interact, decohere, and settle into collective behavior. The quantum rules have not vanished. They have become the material from which classical regularity emerges. Temperature itself is collective. No single isolated particle possesses temperature in the ordinary thermodynamic sense. Temperature describes distributions of energy across many degrees of freedom. Pressure emerges from countless molecular impacts. Sound emerges from coordinated motion. Rigidity emerges from bonding and quantum statistics. The everyday world is not separate from the quantum world. It is what the quantum world does when many parts interact under ordinary conditions. This emergence is one of the gentlest answers to the question of why we do not see superpositions everywhere. At human scale, information spreads rapidly. Interactions average over microscopic details. Stable patterns become robust. Classical physics appears not because quantum mechanics stops, but because large systems organize its possibilities into predictable behavior. Newton's laws remain magnificent approximations. A falling object follows a trajectory so sharply concentrated that quantum spread is irrelevant. Maxwell's equations describe light fields containing enormous numbers of photons. Thermodynamics works without tracking every molecular state. Classical theories are not wrong in their domains. They are higher-level descriptions emerging from deeper rules. Quantum physics did not destroy the old world. It explained why the old world works as well as it does. The same relationship appears in biology. Molecules bind according to quantum chemistry. Enzymes shape reaction pathways. Photosynthesis begins when pigments absorb photons. Vision begins when light changes a molecule in the retina. Smell depends on molecular interactions. DNA is stable because of chemical bonds, while mutations can begin with microscopic events. Some biological processes may exploit tunneling, coherence, or spin-dependent reactions in limited ways, and research continues into how significant those effects are. But life does not require vague quantum mysticism. Its ordinary chemistry is already entirely quantum mechanical. Every heartbeat depends on ions moving through protein channels whose shapes and energies are determined by electron states. Every breath brings oxygen molecules whose bonding cannot be explained classically. Thought itself occurs in matter stable only because of quantum rules. Quantum physics is not somewhere beneath life. It is inside the possibility of life. It also sets limits. Atoms cannot be made arbitrarily small while retaining the same identity. Measurements cannot reveal incompatible quantities with unlimited precision. Unknown states cannot be copied perfectly. Signals cannot be sent faster than light through entanglement. Energy levels, spin outcomes, and exchange symmetries restrict what matter can do. The universe is creative because it has rules, not because anything is allowed. Those rules produce astonishing variety. A handful of particle types and interactions build nuclei, atoms, molecules, crystals, liquids, stars, planets, cells, and minds. The complexity does not come from each level needing a new set of fundamental ingredients. It comes from arrangements, collective behavior, and emergence. Quantum physics reveals how much can grow from a small foundation. There are still unanswered questions close to that foundation. Why do the elementary particles have the masses they do? Why are there 3 generations of quarks and leptons? What is dark matter? Why is the cosmological constant so small compared with naive quantum estimates? Why did matter survive over antimatter? How should measurement be understood? Is space-time fundamental or emergent? Can gravity be quantized in the same framework as the other forces? These questions are not cracks showing that quantum physics has failed. They are boundaries showing where the successful theory meets a larger unknown. The standard model may be an effective theory, accurate within the energies explored so far, but part of a deeper structure. Quantum mechanics itself may remain exact, or it may emerge from something still more fundamental. Experiments will decide where experiments can reach. Future clues may come from precision rather than enormous energy. A tiny mismatch in the magnetic moment of a particle, a forbidden decay occurring rarely, an unexpected pattern in neutrinos, a dark matter signal, or a measurable loss of coherence could open a new chapter. The history of quantum physics began with small mismatches. A furnace spectrum would not fit. A metal cared about the color of light. An atom emitted sharp lines. The anomalies looked narrow. They changed the picture of reality. It is possible that another quiet discrepancy is already waiting in data, not yet recognized as the doorway it will become. That thought brings the story back to the room. The device carrying this voice relies on semiconductor band structure. Its clock is synchronized through technologies rooted in atomic transitions. Its display uses photons produced or controlled by quantum materials. Some of its memory technologies store charge in microscopic structures where tunneling and quantization matter. The network that delivered the sound likely used laser light in optical fiber. Quantum physics is not hidden because it is rare. It is hidden because it is everywhere beneath familiar behavior. The atoms in the room do not need to decide whether they are waves or particles in the language of ordinary objects. They simply evolve according to quantum rules. Electrons do not become confused by uncertainty. Photons do not wonder which slit they crossed. Nature does not find its own behavior paradoxical. The paradox belongs to the meeting between quantum structure and human intuition. And perhaps that is part of the wonder. The mind evolved to guide a body through a world of stones, branches, faces, distances, and weather. It was not shaped to imagine complex amplitudes or Hilbert spaces. Yet through mathematics, instruments, and patient experiments, that same mind learned to predict the behavior of atoms and light with extraordinary precision. A species built for the visible world found a doorway into the invisible one. The doorway did not reveal a smaller copy of everyday reality. It revealed a realm where possibility interferes, properties depend on experimental context, identical particles lose individual labels, and separated systems can share a state that belongs only to the whole. Still, from that unfamiliar realm comes everything familiar. The solidity beneath you is supported by quantum exclusion and electromagnetic fields. The warmth around you is carried and exchanged in quanta. The darkness of the night is crossed by photons from distant stars. Inside those stars, tunneling helps nuclei fuse. In your body, spins respond to fields, atoms bind into molecules, and electrons occupy states that keep matter stable. Quantum physics can feel unsettling because it removes the simple picture of a universe made from tiny pieces carrying definite properties along definite paths. But it also offers a quieter picture. Reality is not less ordered than we imagined. Its order is simply deeper than the categories first available to us. There is certainty in the probability law. There is structure in uncertainty. There are exact limits on what can be copied, known, or signaled. There are symmetries strong enough to create particles and conservation laws. There are equations that predict the colors of atoms and the magnetic moment of an electron with almost unbelievable accuracy. The quantum world is strange, but it is not chaotic. And now the story can become smaller and slower. Somewhere in the device nearby, electrons occupy energy bands in a crystal. Some are redirected by gates too small to see. Somewhere in the room, a warm surface releases infrared photons. Molecules in the air rotate, vibrate, and collide. A distant radio signal carries energy in quanta. None of these events asks for attention. They continue whether the room is watched or dark. The wave functions of microscopic systems evolve. Environmental interactions spread information. Macroscopic objects remain steady. The classical world settles around the quantum one like a calm surface over deep water. You do not need to choose an interpretation tonight. The universe can branch, collapse, relate, guide, or remain described only by the predictions, and the equations will continue their quiet work. Physicists can return to the argument tomorrow. For now, it is enough to know that the world beneath appearances is rich, precise, and gently strange. A photon may cross a dark room and end its journey in one molecule. An electron may tunnel across a barrier no classical path could cross. Two distant particles may preserve a correlation that no local instruction can explain. An atom may wait an unpredictable time before decaying, while a billion atoms together follow a perfect curve. From such events, stars shine, clocks keep time, matter holds its shape, and technology carries a human voice through the night. The smallest scales do not feel small when their consequences fill the universe. And so, as the mind becomes quieter, the quantum world can remain awake on its own. It does not need to be pictured completely. It does not need to become ordinary. Its probabilities will add, its amplitudes will interfere, its fields will fluctuate, and its atoms will remain stable. The room around you can stay still because countless quantum processes are already doing exactly what they do. Sleep well. Good night.